Okay. Presentations of papers, Thursday, Friday. If there is any mistake, let me know after this lecture. And for now, we will restart with Professor Shlyapnikov.
Thank you. Hello. Do not know whether I should say good morning or good afternoon. It's 11 o'clock. Yes. Okay, so what I'm going to do today, yes, I see more or less the same number of people as yesterday. Yes, maybe a bit less, but it's okay. I will continue with dipolar bosons. Yes. Yesterday, I discussed with you in the end of my lecture, Bose-Einstein condensation of dipolar particles. Yes, particles which have a dipole moment and interact with each other via the dipole-dipole interaction, V-dipole, unit divided by R cube. Aside from that, there is short-range interaction. And then what I showed you actually is that the excitation spectrum looks like that, yes? And when G, the short-range interaction, is larger than dipole moment in the square, multiplied by a numerical coefficient, I get a dynamically stable condensate. If not, then there are complex frequencies in the spectrum, which means instability. The complex modes, they grow, and the condensate is destroyed, yes? So, nevertheless, dipolar bosons, the Bose-Einstein condensation, and possible new macroscopic quantum states were still attracting a great interest. For a very simple reason, because in reality, in all experiments, these dipolar bosons are in a confining potential, in a harmonic potential, yes? For example, here, I have a confining potential which is of a cylindrical form, yes? This is the transverse frequency, longitudinal frequency, rho and z are the coordinates, yes? Then, of course, what we do, we write down the Gross-Pitaevsky equation, yes? Which now looks this way. This is the harmonic potential, this guy, this is short-range interaction, yes, this is the dipole-dipole interaction. And of course, what people were all the time trying to do is to solve this Gross-Pitaevsky equation, yes? And you can do this in various ways. The simplest way for many, many people was to jump at a computer and just manipulate and trying to find the solution of the Gross-Pitaevsky equation. But before calculating the shape of the condensate wave function, it's important to understand what are important quantities here. And the first important quantity is the so-called effective interaction between particles, which is just the interaction potential multiplied psi0 in the power of 4. So this is G, psi0, 4, D3R. This is the contribution of short-range interaction, and this contribution is the contribution of the dipole-dipole interaction. Yes? And then, if this guy, V effective, is positive or it is negative but smaller than the trap frequency, which means level spacing between the trap levels, yes, then the condensate is likely to be stable, yes, for example, for 0J, yes, where this is 0, the instability at low momenta is suppressed when the number of particles is smaller than a critical value. It does not at all mean that it's completely stable, but that's what it is like here. Then, what you have, you may solve Gross-Pitaevsky equations, yes, and then you find out that, for example, if your trap is spherical, yes, then the cloud will be elongated in the direction of the dipoles because of the anisotropic character of the dipole-dipole interaction, yes. This is the ratio of the axial to radial size, which increases with increasing the dipole-dipole interaction, yes? If the trap is like that, yes, then V effective larger than 0, yes, the cloud will look like that. And then this is, again, the ratio of the axial to radial size, yes? So, but how to handle all this? Is there a transparent way of doing so? And the answer is yes, there is. And this actually has been done in a very nice work of Claudia Eberlein, Duncan O'Dale, and Stefano Giovanazzi in 2005. Yes, our paper with Peter Zoller was somewhat earlier, but they did a much better job than us. Yes, what they have done, they introduced this quantity, average value of the dipole-dipole interaction, yes, and they represented the dipole-dipole potential, which is unity divided by R cubed. You may represent it in the following form. Second derivative with respect to Z of R minus R prime, yes, and this delta functional term, yes. Then, using this, yes, what they have shown that for a large number of particles, you have the so-called Thomas Fermi BEC. The condensate density is just a parabola, inverted parabola, exactly in the same way as it is for the short-range interaction, but the parameters of the parabola are different, yes? If J is larger than 4 pi d squared divided by 3, this is, let me remind you that this is a critical number for the uniform condensate, yes? Then, in this case, the condensate is stable at any number of particles, yes, whatever happens. So very remarkable work, and those of you who are dealing with Bose-Einstein condensation, yes, and are interested in dipole particles, magnetic atoms, or polar molecules, should definitely read this paper. You know, it's absolutely remarkable that what you do, you say that I know from this paper that the shape of the condensate wave function is inverted parabola. Yes, it's like that. Yes. Let me assume this form, yes, that, and then depending on the trap, I have the radial size and the axial size. Substitute this guy in the Gross-Pitayevsky equation, and then find these parameters. And then I find the result, yes? That's what it is. Now, when we know that this is correct, we can do things in this very simple way. That's what they have done. And so, this is this paper, yes, and for those of you who are interested, I advise to have a look there, yes. So these are the examples, the ratio of the radial to axial size as a function of dipole moment in the square divided by G, so the ratio of the dipole-dipole to short-range interaction, yes, and that's how it goes. Here is the instability, yes, right? And the role of dipole-dipole interaction has been tested experimentally by experiments of Tillman-Pfau with magnetic chromium atom. So what you do, you create a cloud, and then the cloud expands, yes? And the expansion of the cloud, the shape of the expanding cloud, is somewhat different compared to the case of only short-range interactions, yes? For example, for the dipoles like that, it's like that. For the dipoles like that, it's like that, and so on and so forth, yes? So here I compare the size of the cloud with dipole-dipole interaction, with the shape of the cloud without it. And that's what they have done experimentally. The effect of the dipole-dipole interaction, of course, in these experiments was not big, it was small, just because it's a magnetic dipole-dipole interaction, and therefore it's not dominating. But this was like that. So, Now, I turn to something very interesting. You know, people were wondering for quite some time what kind of interesting quantum states they can obtain with dipolar bosons. And one of the first works on this subject was the work whether we consider G, the short-range interaction, smaller than G dipole, this guy. Again, in the uniform three-dimensional case, under these conditions, the dipolar Bose-Einstein condensate would be unstable, but people considered here extreme pancake, which means that there is a confinement in the z direction, and in the perpendicular directions the motion is free. Omega radial is 0. The characteristic length is L0, harmonic oscillator length in the confined direction, yes, and then V dipole plus G, this is the interaction, G is larger than 0, and then what people have done, and I will tell you later who these people are, they found the ratio of the excitation energy to the frequency in the z direction, and it turned out that it goes like this, or it goes like this, has roton, as a function of q, the momentum in the direction rho. In this rho direction, the motion is free, therefore the wave vector or momentum is a good quantum number, and excitation energy depends on this q, yes? For example, for various values of g divided by g dipole, you have various curves. What is interesting here is that there is a case where the spectrum shows the so-called Roton minimum, yes? And this is very interesting. This resembles the situation with elementary excitations in superfluid helium, which people worked on for tens of years, yes? Here, in liquid helium, this spectrum is fixed. You can only change it a little bit by changing the pressure. Here, what you can do, you may engineer the position of the roton by varying the ratio of the short-range to dipole-dipole interaction. And the short-range interaction constant can be varied by using Feshbach resonances, which Jörg discussed with you in his lectures. Yes. So that's what it is. And then what is interesting here is that in principle, the Roton minimum can be put equal to 0, which was the dream of people dealing with superfluid liquid helium, yes? And in this case, what one can show just by solving the Gross-Pitayevsky equation, that you get instability. The system becomes unstable, yes? Here is the ratio of this critical G to G dipole. This is the short range, yes? So you get the region of rotonization, and then you get instability, yes? And this has been done in this paper, Luis Santos et al. Et al. Is Maciek Levenstein and myself, and this paper has been done in 2003, yes? I do not present here any formulas from this paper, but if you are interested in what people could do 16 years ago, just have a look in this paper. It's interesting. It's not the best paper among papers on dipolar systems, but it was actually one of the first papers where interesting phenomena has been expounded, yes? And two people in the last rows, do you hear me very well or not? Is it okay? Okay. So, after producing this work, we started to think whether this instability can be suppressed by confining the system to 0-point oscillations in this tightly confined direction, to harmonic oscillator length. Yes, and that's what it was done, yes, in this work. Then we have short-range interaction G plus dipole-dipole, yes, and then we may consider G smaller than this guy. Then for small momenta, the Fourier transform of the interaction potential can be expressed in this way, where the first term comes from short range and the second comes from the dipole-dipole interaction. C is unit divided by G, G cancels, so it's D squared divided by the difference in the momenta, yes? And then what you do, you write down the Hamiltonian, yes? Then what you do, assuming a uniform condensate, you do the Bogoliubov transformation, which I showed you in the previous lecture for uniform BC, and you find the excitation spectrum, which has a Roton minimum, or may have a Roton minimum, which can be put equal to 0. The excitation energy is given by this relation. Here it is in the square. And then the position of the Roton follows from this formula, where psi is the famous healing length, which I introduced yesterday. Yes. Then, what is interesting is that rotonization occurs when C is larger than this number, which is larger than 1, multiplied psi, and smaller than psi. And when the Roton minimum touches 0, it does it for C equals psi, and then K Roton is this. It turns out, and this has been checked numerically, yes, that for C larger than psi, we have a collapse. This also follows from the relation for the excitation energy, yes? And, sorry?
Sorry, I didn't get, where is the Roton?
Roton is for a very simple reason. There is a short-range interaction which is positive, yes, and then there is part of the dipole-dipole interaction which is negative due to the anomalous scattering. So the interaction depends, so it's constant, let's call it A minus B multiplied K, yes, where K is the momentum. Yes, this is because of the momentum dependence, yes. The interaction, the Fourier transform of the interaction potential is momentum dependent. In contrast to, let's say, short-range interacting gases, where you have van der Waals at large distances, and you just have this A, yes. The presence of this term is crucial, and it is this term, it comes from the so-called anomalous scattering, yes, scattering of particles coming from distances of order de Broglie wavelength, yes, which makes the rotonization possible in these systems, yes, only due to this case, yes. And then what happens is that here again you get collapse, and several people checked that. I was one of those people, Nigel Cooper and Cominas. They did a very nice work where they have shown this clearly. Yes? Okay. So, then, why people were trying this system? They were trying this system, in particular myself, because we had in mind the formation of a stable super-solid state. Before I continue with dipolar bosons, I would like to say something about this super-solid state, yes? In order to do so, I will actually, yes, show you another file, yes? What is supersolid state? It has been predicted a long time ago. Actually, the first person which predicted the presence of such supersolid states is Gross, the same Gross as Gross-Pitaevsky equation. And this prediction has been made in 1957, even before writing down the Gross-Pitaevsky equation, because what he did, he considered classical field equations. So now we have the following understanding. Imagine, please, that in free space, no external potentials, just free space, the condensate wave function acquires a lattice structure on top of a uniform background. So it looks like that. There is a uniform background, and uniform BC is typical in free space. But on top of that, you have this oscillatory structure, lattice structure. And the lattice can be a stripe phase, triangular phase, or whatever. Yes? That's what we now understand as a supersolid state. And the question which people raised is, for which systems this supersolid state can exist, yes, and what are transport properties, superfluid properties? Because the term supersolid, it has two roots. Solid, which means that there is a crystalline structure of the condensate wave function, although it's a dilute gas, yes, and super comes from superfluidity. The system is supposed to be superfluid, at least at sufficiently low temperatures. And you see that the existence of this state is amazing. You have free space, no external forces, no nothing. And surprisingly, in this free space, the condensate forms this type of structure. And if I look in the work of Gross and then in the work of these people mentioned here, yes, this is all due to the interaction between particles. Let's say when the interaction is strongly momentum dependent or significantly momentum dependent, this may induce the presence of this so-called supersolid structure, yes? And
so it is a short-range interaction or long-range?
Of course, if it is just short-range interaction, just constant, then you don't get supersolid state. It's constant plus something, yes? So it's not simply a short-range interaction, yes? There should be an interaction tail. If you put short-range interaction, the just constant, you don't get supersolid state. And that's why when I was considering an attempt, in particular an attempt of myself, to obtain the supersolid state, we were using the momentum-dependent Fourier transform of the interaction potential. Yes, and not only us, other people have done that. But the history of the problem is quite interesting. Actually, after all these people mentioned above, yes, there was a very interesting work of Lev Pitaevsky, the same Pitaevsky who is re-editing 10 volumes of Landau-Lifshitz, who is a professor at the University of Trento in Italy, yes, the pupil of Landau, absolutely remarkable guy. In the age of 86, he is still doing physics and writing papers, yes. Many people in this age are just take a horizontal position and relax. He continues to work. This is a very good example for young people. Yes. So what he has done, he considered liquid helium-4 flying in a capillary with the velocity which is larger than the critical velocity. And this is the spectrum. This is the Roton minimum, yes. And when the velocity is 0, the Roton minimum is above 0. But then, in the moving frame, when I add the velocity, the Roton minimum touches 0, yes? And then, what Lev has concluded is that there will be a density wave, yes, in the moving frame, like stripe supersolid state. In a later, so this will be the density, yes? So he did it analytically, or almost analytically, and in a much later stage, when Lev was already in Trento, together with several other people from that laboratory, they did numerical calculations and obtained this structure. Absolutely remarkable work, which unfortunately has not been implemented in experiments. Why? Because I was talking to experimental people, in particular to Sebastian Balibar, who is a remarkable experimentalist with liquid helium. And they say that it's extremely difficult to make this picture. I have a capillary in liquid helium, and I arrange the flow with the velocity larger than the critical velocity in such a way that nothing else happens. That's what it was. Then, what people have discussed, they have discussed in literature what happens if in liquid helium I just apply pressure, what happens with the Roton minimum and so on, can it be put lower, higher? Then there was the idea of Feynman, why the Roton minimum appears in liquid helium, yes? He just calculated the structure factor and said that this follows from the structure factor, yes? Then people were assuming to apply negative pressure or acoustic pulses or increase the pressure, get metastable liquid and so on. But what they have shown, and this was in the work of Kirchnis Nepomniachtchi, which was mentioned earlier on my slides, is that when the Roton minimum is at zero, or almost at zero, the system becomes unstable, yes? So the same story, which we repeated with dipolar Bose-Einstein condensates together with Louis Santons and Maciek Levenstein. The system is unstable. So in a much later stage, yes, so, okay, this is still the work that I already mentioned, yes, collapse of the supersolid state in a dipolar BEC in quasi-2D geometry, yes. But people also considered, let's say, soft core two-body potential, when the two-body potential is like that, and there is a soft core. And then it has been shown by several people, yes, that if the tail is behaving itself as unit divided by R in a certain power, not very large, then there can be a stable supersolid state. They showed this by the mean field theory, and people like Guido Pupillo, they never trust mean field theories because they do Monte Carlo. When Guido Pupillo did Monte Carlo, in one of his calculations, he recovered, let's say, these dense supersolids, dense droplets of supersolids. And there is a review article in 2012 by Bonanzeni and Prokofiev, which covers the research on finding supersolids in previous years. Yes, that's what it is. But what is interesting, and I will continue with this later, is the experiment. You know, Tillman-Pfau did experiments with dysprosium atoms, yes, which is a strongly magnetic atom with a magnetic moment of 10 Bohr magneton, yes. And then what he obtained experimentally, he obtained droplets of these dysprosium atoms. As I already told you in the previous slides, that for the dipole-dipole interaction and in a trap plus short-range interaction, there should be a critical number of particles. Above this critical number, the effective interaction becomes negative and the system should collapse. Yes, that's what it was in my previous slides. And you know, usually what happens with us is the theoreticians predict something, then experiments show that this is not the case, and the theoreticians have overdone. In this experiment, it was the other way around, yes? According to theory, when they identified the number of particles in each droplet, it was such that for this number of particles, the droplet should collapse, but it did not, yes? So it was exactly the other way around. A very interesting experiment of Tillman-Pfau, and now I continue with this, but in order to do so, I again go to my previous file, yes. And okay. No, it's not this file. Sorry. It should be this one. Yes. Okay. So that's what was experiment of Tillman-Pfau. But other people also did experiments, in particular, the group of Francesca Ferlaino. Yes. This is the group which is at the University of Innsbruck. Yes. And by the way, just a side remark. This year, in September, actually, some 2 weeks ago, yes, Lev Pitaevsky and Sandro Stringari got the senior Bose-Einstein condensation prize, yes, and Francesco Ferlaino got a junior Bose-Einstein condensation prize, yes. So they were, and Francesco Ferlaino did the following experiment. They had elongated condensate of erbium atoms, 7-Bohr magneton, magnetic moment, like that. And then what they have found by using the Bragg spectroscopy, they have found the excitation spectrum, yes? In this direction, the system is practically untrapped or very weakly trapped, so the momentum is like this. So the spectrum behaves like that, yes, there is a Roton minimum, and that's what they have found experimentally. And they started to advertise our paper with Luis Santos and Maciek Levenstein that we predicted 16 years ago or whatever. Now they have found experimentally. Although, being honest, we considered a quasi two-dimensional geometry, and they are in the quasi 1D. The system is elongated in one direction. But it was interesting that in this case, you have Roton-Maxon spectrum. And interesting things were happening in this experiment when the Roton was very close to 0. Now I turn to this. So, in order to turn to what happens in this case and why Tillman-Pfau obtained these stable droplets, bosocondensed droplets of dysprosium atoms, we have to turn to some theoretical investigations. Yes. This is the Hamiltonian in free space. This is the kinetic energy. This is the short-range interaction. This is the dipole-dipole interaction. And there is one more term which contains gamma QF. This is the term which is coming from quantum fluctuations. And this term originates from these terms, psi prime, psi prime, psi prime squared, psi prime squared, which come from quantum fluctuations, if I take them into account and write generalized Gross-Pitaevsky equation. In the energy functional, then, I get an extra term which is proportional to this gamma QF, which is G multiplied AQ, A in the power of 3/2, unity plus dipole-dipole interaction in the square. And this is 3D scattering length for short-range interaction. G is this, yes, epsilon dd is A dipole-dipole, D squared divided by H bar squared multiplied the mass. And this is absolutely amazing that one should take into account this gamma QF, the term originating from quantum fluctuations, and put it in the Gross-Pitaevsky equation. Absolutely counterintuitive idea, because usually what people are doing, They have Gross-Pitaevsky equation, ordinary one. They solve it, then they solve Bogolyubov-Dejean equations with the obtained condensate wave function and obtain excitation frequencies. And that's what everybody was doing tens of years. And in this case, for the dipoles of Tillman-Pfau, you get the instability. But you know what happens? That in this paper, absolutely remarkable paper by Dima Petrov, which was published in 2015, he considered a different system, two-component Bose-Einstein condensate, but it doesn't matter, the idea is there. What he says is that if there is a soft mode, yes, and it may become unstable, what I would do, I take into account all other modes, calculate the outcoming quantum fluctuations correction, substitute them in the generalized Gross-Pitaevsky equation, and then I get that this mode is no longer unstable. Yes, that's what it is. In a later stage, what happened is that, so this is, yes, so this is just from here, yes. What people have done, aside from trivial solution, they did a Gaussian ansatz for the Gaussian shape of the condensate wave function, and they found droplets elongated in the direction of the dipoles, yes. These are just some formulas from the work of Tillman-Pfau, how they were explaining the experiment, yes. That's what people have done. Of course, not everybody was believing that this is correct, you know, because this contradicts to everything what has been done before, yes? And when you minimize the energy, you get that the size of the condensate in the radial direction in the square multiplied sigma in the z direction is proportional to the number of particles. Energy is proportional to minus n. And then density is this, does not depend on the number of particles. You get so-called liquid droplets. When you increase n, energy is the same for two or more droplets far from each other. Yes? And then if you increase n, yes, above a critical value, this leads to 2, 3, 4, 5 droplets and so on. Yes? And then all this is consistent with, let's say, experiments in the group of Tillman-Pfau. Yes? Of course, so these are just these droplets, yes, which I have here, right? And then what has been done by people, actually Luis Santos and his group, they did calculations including the trapping geometry and so on, and they confirmed the idea that these droplets are stable, but Saito did Monte Carlo calculation for a singlet droplet, and he confirmed what follows from the theory of Dima Petrov. Yes? So this Petrov idea, which initially was questionable, very many people questioned this idea, it has been confirmed by Monte Carlo calculations of people. Yes? So I would say that, no. Okay, right. But what is interesting here, that in these experiments of Tillman-Pfau, there were just droplets, and the distance between them was sufficiently large so that this was not a supersolid state. Yes, they were not coherent. And this may be, since I think I have a little bit of time now, I will show you a different file. Yes. Right now, where I am. I'm here. Yes. that's what has been done by people. Yes. Here, I just show you that people were also saying that maybe these droplets are stable because there is three-body repulsion, but this turned out to be inconsistent. Yes, and then this Li Huang-Yang correction, what I was talking about, it is called the Li Huang-Yang correction, is proportional to density in the power of 5/2. It's repulsion. So if there is attraction, which is proportional to n squared, the repulsion density in the power of 5/2 at large densities beats this attraction, and therefore the system is stable. And this follows from the work of Petrov, and then, right, they studied dynamics, and Saito did Monte Carlo calculations, and then these are pictures of these droplets from Yun Li, yes. This is the person who was doing a lot of calculations with, let's say, dipolar condensates and so on. Now she is one of the editors of Nature Physics, yes. And then, of course, this is not a super solid. And there was a project of Tilman Pfau how to get super solid. I turn to this slightly later. But now, what I can do, I can say that there were very many attempts to obtain a repulsion at large densities. Yes. For example, one of the ideas belongs to the same people, yes, which is Petrov, Zheng Lu, Yun Li, and myself, yes, that if you have two layers, yes, right, and there is tunneling, yes, then the two-body coupling, G2, can be made small or even zero, and three-body coupling is repulsive, and it turns out like this. So the presence of this layer, where one of the particles from here virtually tunnels here, forms a three-body system. With this induces a three-body repulsion. Yes, this was the work of Petrov, and in a later stage, these people, they introduced condensate wave function in the form of triangular supersolid or stripe phase, yes, like this, and they obtained that there is a stable supersolid state, yes, and in this work, absolutely amazing calculations have been done showing that the mean field approach is not always correct, and you have to do at least simulation of the Gross-Pitaevsky equation in imaginary time. Yes, now this is already different. Yes, that's what it was. But this was just an intermediate step in, let's say, theoretical studies, yes, and now I continue. Yes, so it was actually here. Now I will continue, yes, and turn to the work that has been actually done this year in 2019 and was just published very recently. What happens is the following, that three groups, and this is the group of the same Tilman Pfau, yes, right? The group of Giovanni Modugno, in Florence, and the group of Francesca Ferlaina in Innsbruck, they obtained again these dipolar droplets, but what they have shown experimentally, that these dipolar droplets are phase coherent. Compared to previous experiment of Tillman-Fau, simply the distance between droplets was smaller, yes, and which allowed the system to get phase-coherent droplets. So it was a very big step forward, but we understand, and this I would like you to fix in your brain, that phase coherence and superfluidity are not equivalent to each other. Phase coherence is a completely different physical phenomenon. If the system is phase coherent, it does not at all mean that it is superfluid. Yes? For example, consider Bose-Einstein condensate of ideal bosons, non-interacting. Everything is phase coherent, even if you put it in a double trap, everything is phase coherent. But the system is not superfluid. Yes? Therefore, superfluidity and phase coherence, these are completely different phenomena. Now, I come to the question, what to do in this case? Yes? And some of the work has already been done, and some of the work is still in progress. Yes? If you have a phase-coherent array of these droplets, how to show whether the system is superfluid or the system is not superfluid? Who has answers to this question? Who has ideas? What I should do to show that the system is superfluid or to show that it is not superfluid? Any ideas? Also, senior people are allowed to answer. Yes? Huh? Yes, you can rotate. So what? Rotate, and what after that? Yes, in principle you are right, and there can be an experiment where you measure the moment of inertia, yes, like people have done in liquid helium. And so this is possible, yes, but the measurement of the moment of inertia by doing this is a very difficult task for dilute gases, yes. So although this idea is in the agenda, yes, what are other ideas? Yes? Are there other ideas? Young people and senior people, please try to respond to this question. We have time. Yes? And I see that even how to say, I do not dare to say old generation, yes? Because at least Yokval Ravin is the same old as me, yes, almost. Sorry? Yes, Misha is a bit younger, and Roman, I think, is even younger than Misha. But please, young people, usually young people come up with strange and sometimes useful ideas. So if you have an idea how you can show the presence or absence of superfluidity in this phase-coherent array, it's quasi-1D array, of dipolar droplets, this will be very, very useful. Yes, but let me continue now. So, in order to induce your questions and thinking, I will show what people have done. What they have actually done, they have measured the excitation spectrum of the system. And here, where is mine? Here, I present this excitation spectrum, and here, what I just do, I simply increase the ratio of the dipole-dipole to short-range interaction, yes? That's what they have done experimentally, yes? And this is what they have, you know? Here, they have a uniform condensate, low energy excitation. You have a condensate in a trap, so okay, this is just frequency of the lowest excitation, so it's there. And then, at some point, this excitation splits into two, the upper one and the lower one, yes? What this is? People say, and there were theoretical investigations, I'm not sure that they are very good, but they have been done, yes, that this is the point where you have a transition from a uniform Bose-Einstein condensate to a supersolid state. And this upper branch, this is just ordinary branch, let's say oscillations of my condensate. And this lower branch, it describes oscillations of the lattice structure with respect to the fluid, yes? You have this stripe phase, yes, on top of a uniform condensate, yes? And then this guy, it may oscillate with respect to this fluid. And this is the lowest branch, yes? That's what people say, and this is what has been measured in all three experiments, yes? So I would advise you to have a look in these papers, especially in the paper of Giovanni Modugno, which is done together with 2 or 3 theoreticians from the group of Stringari, yes, where, you know, it's an experimental paper which to a large extent is theoretical, yes. So do not know how good or how bad this is, but in the paper there are very many useful thoughts, also the thoughts about the excitation spectrum, yes, right? That's what it is, and I simply advise you, for those who did not yet write down, these are 3 papers, yes. They are now already published, just now, these two papers in Nature and the paper of Francesca Ferlaina in Phys Rev Letters. But they are in the archive, you may easily find them, yes. That's what it is. And nowadays, what happens is that I especially dedicate, let's say 5, 10, maybe 15 minutes to the discussion of what is happening now in the field. That people, of course, this is quite nice, that people obtain this. It's a confirmation that yes, it is very likely that this is a transition from uniform condensate to a super solid. Do not pay attention on this, yes? But it would be nice to actually show that the system is really superfluid, yes? And with this, it is also nice to understand how the superfluidity occurs. Why? Because there is this lattice structure and uniform background. How the superfluid flow goes. Do they flow with the same velocity? Or, let's say, lattice structure is standing and this guy is flowing with a certain velocity, or they flow with 2 different velocities, yes? And Francesca Ferlaino says that the last option is likely to be the case with different velocities. Because if I look at this picture, yes, it says that the critical velocity for this guy, for this excitation and for this excitation, they are different. This excitation, actually, if I will do everything in the, let's say, in free space, yes, the oscillations of the lattice structure with respect to, let's say, the fluid will have a lower critical velocity, smaller critical velocity, yes? So what does it mean in the experiment if I were able to arrange a flow of a superfluid through a capillary? We don't know. Is it such that, let's say, oscillations or motion of the lattice structure with respect to superfluid, with respect to the fluid, that it ceases or what? We don't know. Yes? So the question is actually fundamental. How the superfluidity of a supersolid occurs? How these 2 guys are flowing. And one of the options to discuss this is to identify whether one can extract the superfluid density from the experiment. And Francesca Ferlaino did a very, very, very nice experiment trying to measure the dynamical structure factor, yes? And now they say, or they think that from the dynamical structure factor, you are able to extract the superfluid density, yes? And this is actually very important, So at this point, I would rather raise a question to you. What would you do in order to identify the superfluidity and how it occurs? Who of you are experimentalists? You are. Okay, quite many, yes? So imagine that this experiment is in your hands and you have dysprosium or erbium and you have this. What would you do experimentally? Okay, silence. And I completely understand why you are silent, because all other people, including very senior people, are also silent at this point, yes? But what the group of Francesca Ferloina did, they were silent also a little bit, but they have done the Bragg spectroscopy, trying to extract the superfluid density from the Bragg spectroscopy experiment. And they say that they can do it, likely can do this, and now we're analyzing whether this is really the case or not, yes? Because extracting the superfluid density from the experiment would be crucial. Of course, this does not answer the question how the superfluidity occurs. And in particular, what happens if the velocity of the fluid is larger than the critical velocity of these type of oscillations. Lattice structure with respect to the fluid, and smaller than the critical velocity just for the fluid. Yes. So actually, this we don't know. Maybe what is supposed to happen, that this will lead to the deformation of the lattice. Yes, or disappearance of this lattice, so that the system just becomes an ordinary superfluid. These are the ideas that I'm now having in mind, yes? And with these ideas, I am close to the end of my story of today, yes? I told you about the ongoing experiments with dipolar bosons, about what people are thinking, what is supposed to happen, yes? And now I would say that very many theoreticians are jumping in this field, yes? Usually, if something interesting is happening experimentally, then God knows how many theoreticians jump there, yes? This is a typical phenomenon, yes? And I cannot exclude that some of the theoretical efforts of these guys will be useful, yes? So, therefore, let us wait 1, 2, 3 months and something will appear in literature, yes? Maybe even something useful, yes? So, if you do not have ideas how I measure superfluidity of the supersolid, maybe you do, aside from the moment of inertia, yes? Is there something else what you as an experimentalist can do and would do if the experiment is in your hands? Imagine that the experiment is in your hands. What would you do? Huh? Then tell me, what is wrong in what I'm saying now? Imagine that you have a capillary, yes? Your superfluid, and this supersolid guy, is flowing with velocity v. Yes, and you may change this velocity. It is in your hands. And then it's like capillary with friction. So it's not a perfect wall, but there is friction. So in principle, which may induce the appearance of excitations. Yes. What is wrong with this experiment? Why not to do this experiment with a cold gas of let's say, dysprosium or erbium? Yoke, why not to do this experiment? Is it stupid what I'm saying or not? Sorry? Well, it's a magnetic capillary. It's a magnetic, for example, magnetic, yes? With real capillary, I don't know. If you mean the same capillary as they have with liquid helium, then the answer is likely not. But probably it's a magnetic atom waveguide, yes. And you are sorry? For example, there is nothing wrong with this experiment, or something is wrong. Huh? Okay. My answer to this question is I don't know whether something is wrong with such an experiment or not. Yes. Probably these people, Francesca Ferlaina, Tilman Fau, Giovanni Modugna, they can give a better answer than me. Yes. But you know, telling you about all these new things appearing in the field, I would like that I'm already talking 1 hour, yes, and what I would like to do, since I have told you very many new things, I would like to listen to your questions. Yes, thank you.
Can you give a better insight about superfluid density? It's like, do I have a superfluid, therefore it's going to flow?
Yes.
At the same time, I have a density, so I have a gradient. So can this be considered as a...
Yes, this is true. You know, the thing is that usually when you have a uniform superfluid, yes, you have, let me find my choke, you have the total density is superfluid density plus normal density, yes. And then, for the normal density, if you know the excitation spectrum, there is a transparent expression which tells you that the normal density is a function of temperature, yes, and it is something. And you calculate it, knowing the total density and temperature of the system and so on. You calculate this guy, and then superfluid density is just the difference between the total density and, let's say, normal density. And there is absolutely not a problem. Yes, so what is superfluid density in the case of a supersolid? This is still the question which does not have the exact answer. And the reason is that the density is not uniform, yes? In principle, this means that imagine that the lattice structure is standing and the fluid is flowing with a certain velocity with respect to this lattice structure. Due to a non-uniform density structure, particles of the fluid all the time are feeling different density of this structure here, yes? Which in principle may induce the so-called drag force, yes? Right? But when you try to calculate this drag force, you do calculate it, it turns out to be something, but in many cases it is extremely small, yes? So, but what is necessary to do, and that's what many people are doing now, is to first calculate the normal density, yes, for this supersolid state, yes, having in mind that there are two branches of the spectrum and so on, and you calculate the normal density, which can be coordinate dependent, yes, and then you say, okay, the superfluid density and the normal density are related to each other through this relation, yes, and then you obtain the superfluid density, yes. The superfluid density will be just part of the sample which flows without friction, yes, that's what I would do. But again, this is not a trivial task, yes. For example, the coordinate dependence of the super fluid density and of the normal density can be a little bit different from each other, yes? So one has to work in this direction, yes? So this is what my answer to your question is, and the work is now in progress, yes? People are trying to do this, yes? Okay, that's what it is. It's one of the most exciting directions in the physics of dipolar systems to obtain transport properties of dipolar supersolids. It is very likely, what this picture says here, that we're having a supersolid state, but we do not know how superfluid it is, yes? And what we are going to do now is to understand this, yes? Okay. More questions? Yes, please.
You showed to us one picture about the supersolid simulation calculation, and it was x by y. So it was a position, the picture how it should be.
Was it in this file or not? Or in
the
a
other one? The other file.
It was not here, in the other file, yes?
Yeah, it was like a big structure.
Was the simulation?
Yeah, the simulation.
Uh-huh. Okay, so was it? So it was not here. No, it's different. Okay, let me try to find this file and answer your question. Ooh. This will take a few moments. Yes. Yes. Is it this one?
Another one? Well, yes, this one.
Yes.
So this is how a supersolid should look like?
Yes. Yes.
In position? Like
yes. X and Y are positions, and this is for the 2D case. In the third direction, the system is confined to 0-point oscillations.
So if I just take a absorption image, it should be like this?
Yes. That's what, I'm one of the authors of this paper, yes, because this is Zhenkai Lu, Yun Li, Dima Petrov, and here I am, GS, Georgy Shlyapnikov. But saying frankly, all this nice numerics has been done by Yun Li, sorry. That's what it is. And, okay. More questions? Please don't hesitate to ask me what was not clear in what I was saying, yes?
I didn't understand when they measured Bragg diffraction, what exactly did they measure?
The Bragg spectroscopy, you mean? Yes.
What did they measure with that?
By doing the Bragg spectroscopy, people measure the excitation spectrum, yes? And, you just put momentum K and then bump with the other units, K prime, and then you measure the excitation spectrum. And the theory of that and how the experiment should be done, it has been worked out already quite some time ago for uniform condensates, yes? All right? That's what it was. And now this method is used by Francesca Ferlaino to measure this Roton-Maxon structure of the spectrum, yes? There is still a question, and very interesting question, that usually if the transition to the supersolid state, let me again go to my previous file, yes, here. right here. Here are these papers, yes, where I just even presented their archive numbers of these 3 experimental papers, yes. So, you know, as they say, here is the transition from the uniform condensate to a supersolid. Question: assume that temperature is tending to 0, yes, which is to a large extent true. Is it first order transition or second order transition? And the answer to this question exists. If the transition occurs when the Roton minimum just touches 0, then this is the second order transition. If it occurs when the Roton is still above 0, then it's the first order transition, energy crossing, yes? People did not yet properly do this for this particular system theoretically, yes, but experimentally, it is seen that the transition occurs when the Roton minimum is at least very close to 0. With the accuracy of the experiment that exists at the present moment, it's not possible to say whether it occurs when the Roton just touches 0 or when it is still a little bit above 0. Yes, people have to do precise numerical calculations and then just judge whether this is true or not. Okay. Yes. Please. More questions? Yeah. We still have a little bit of time before we go for the coffee break, or it's not coffee break, it's lunch. Coffee break is not supposed to happen. No. Okay. But before going for lunch, yes, ask me nasty questions, bad questions, or whatever, yes. Then we will go for lunch. Just, please. Is everything clear?
I have more.
Uh-huh.
The droplets that they could measure, they could get,
Uh-huh.
they could manage just increasing the density of the BC, or they made some changes in the experiment?
What they do experimentally, they can modify trap frequencies, yes. They can also modify the ratio of the dipole-dipole to short-range interaction. And by modifying this, they observe various regimes for these droplets, yes. So, for example, here you see there is another line here when this branch vanishes. What this means is that when the dipole-dipole interaction becomes very strong, bam, what you get, that this lower branch disappears, you get an incoherent array of droplets, just solid state, I would call it. This is what they say, yes? So, but all these manipulations that they can do, they are done by, you cannot just increase or decrease the condensate density at will. What you can do is put more particles, change trap frequency, change the ratio of the dipole-dipole to short-range interaction. This is what they do experimentally. Okay. People in the last rows, do you have questions or not? Or you are relaxing nicely and dreaming of lunch, yes? Okay. Let me approach you so that I hear very well what you ask. Yes, please.
The rotor modes are characteristic of the dipolar interaction. Okay?
Yes.
But there is another way to induce this rotor mode if we don't have this dipolar interaction. For example, external electromagnetic field interacting for free boson gas, maybe.
So this statement that there are other ways to induce the Roton-Maxon spectrum is correct. For example, we were doing something similar with Subasa Sina also a long time ago, yes, by rotating an elongated condensate, yes, and so on. Yes, so if you just apply an electric, if you have a Bose-Einstein condensate, ordinary one, yes, and then you apply an electric field, what does the electric field do? The electric field induces a dipole moment of each atom, yes, and then you get this induced dipole-dipole interaction, yes, but also there is a quadratic Stark effect which changes the energy proportional to electric field in the square. In principle, by doing this and applying a very strong electric field, you may induce a sufficiently strong dipole-dipole interaction, and then you may get the Rotten-Maxson structure. This is possible. Other strong effects leading to the appearance of the Rotten-Maxson spectrum, right now I simply do not see. Yes. So that's what I would say. But again, if you are dealing with the electric field, even if you have highly polarizable atoms, like alkaline atoms, where the polarizability is several hundred atomic units or whatever, the electric field which you should apply in order to get a significant dipole moment is the electric field which exceeds electric fields are usually employed in the experiment. Because experimentally, what people do, they apply an electric field in order to polarize a heteronuclear molecule. And these are electric fields with, let's say, E, let's say 20, 30 kilovolt per centimeter, yes? If I apply such an electric field to an atomic gas, the induced dipole moment is extremely small. You have to apply the electric field which is much higher than that, yes, in order to get a serious dipole moment, yes? That's what I would say. Experimentally, I was told by Christoph Salomon that they can, in principle, do 50 or even 100 kilovolt per centimeter. But even if it's 100 kilovolt per centimeter, it's not sufficient. You have to do more than that, yes. But that's what my feeling is at the moment, yes. Mm-hmm. More questions or comments or? Yes, I forgot that there is a chairman. Yes. Okay.
There is still time for questions. Otherwise, we can conclude the lecture.
But it's not my last lecture. Tomorrow, I also have a lecture tomorrow on dipole fermions, and you may come up with ideas on what was said at this lecture, yes? What to measure, what to calculate, and so on. Thank you for attention.